System online. Scanning cosmic backdrop. Initiating deep space telemetry. Calibrating for atmospheric interference. Target lock sequence initiated.
Coordinates confirmed. Virgo constellation. Distance, 53.5 million light-years. Target acquired.
6.5 billion. Okay, stepping out of the automated mainframe for a second. Hi, everyone. That staggering number is actually the exact mass of the supermassive black hole at the center of the M87 galaxy compared to our own sun, literally 6.5 billion times more massive. And what's wild is that despite it being over 53 million light-years away, scientists actually managed to capture an image where we can see the dark patch, like the exact event horizon where light is just annihilated from the universe forever.
So how do you even do that? To capture an image at a resolution 2,000 times higher than the Hubble Space Telescope, scientists literally had to overcome the physical limits of our planet. They networked radio dishes across the entire globe, seamlessly syncing their data to build a single virtual telescope the exact size of the Earth. It's just an insane engineering feat, and it is absolutely reliant on the flawless integrity of data, perfectly stitched together from every corner of the planet, just so we can see the unseeable.
But to push our understanding of these massive cosmic events even further, we kind of have to leave the Earth entirely. In 2034, we're launching LISA, the Laser Interferometer Space Antenna, and its scale is almost impossible to wrap your head around. LISA will have an arm length of 2.5 million kilometers. To put that into perspective, that is roughly 6 times the distance from the Earth to the Moon. It's specifically designed to detect gravitational waves, which are basically those ripples in space-time caused when supermassive black holes merge.
Right now, we rely on ground-based detectors like LIGO to spot these gravitational waves. But down here on Earth, our instruments are susceptible to, well, everything. A seismic vibration, a passing truck out on the highway, or honestly, even a scientist sneezing too closely can completely compromise the data. LISA, however, is going to operate in the perfectly silent, undisturbed void of deep space. It's going to capture pristine, completely uncorrupted gravitational data from the very edge of the observable universe.
To guarantee that absolute data integrity, LISA relies on this breathtaking design. Picture this: 3 spacecraft flying in a perfect triangular formation. Inside each one floats a 2-kilogram gold-platinum cube. Now, if a stray particle of solar gas even brushes the outer spacecraft, onboard microthrusters instantly shift the ship to compensate. This ensures those golden cubes inside remain completely undisturbed. It is essentially the ultimate isolation chamber.
But exploring extremes isn't just about chasing massive objects out in the quiet of deep space. Back down on Earth, buried underneath the border of Switzerland and France, CERN is doing the exact same thing, just in reverse. Inside the Large Hadron Collider, they are slamming protons together at 99.9999991%, the speed of light, just to study the absolute smallest building blocks of reality.
Capturing the microscopic data from these incredibly violent collisions requires utterly flawless engineering. Take the Atlas detector, for example. It's one of the key instruments they use to discover the Higgs boson. It is quite literally the size of a building, but unlike a normal building, there is zero empty space inside. It's this marvel of impossibly dense technology, packed to the absolute brim with gas panels, electronic sensors, pipes, and magnets. It cannot have a single gap or faulty section. Why? Because its sole purpose is to perfectly track every single subatomic particle that decays from a collision.
And getting this right is tricky because the magnets required to bend those particle beams are incredibly finicky. These massive liquid helium-cooled superconducting magnets don't even work perfectly right out of the box. They literally have to be trained. Yeah, trained. Scientists painstakingly turn them on and off over and over, training the superconducting loops to withstand extreme magnetic forces so they don't just self-explode under the massive strain.
All of this flawless engineering builds toward an unimaginable data avalanche. When those beams finally cross paths inside the collider, there are a staggering 600 million particle collisions happening every single second. 600 million! And every single one creates a massive, chaotic shower of subatomic debris.
And I think this brilliantly illustrates the sheer rigor of scientific integrity. I mean, you can't possibly record 600 million collisions a second. There's just no way. Plus, most of them are just glancing hits anyway. So CERN's electronics act as this instant brutal filter. They immediately throw away most of the noise, keeping only about 1 in 10,000 hits. Then, deeper in the analysis phase, they discard another 99% of that remaining data. They meticulously distill the utter chaos of a subatomic explosion down to the most unadulterated, purely vital 1% of data possible. Yet even after throwing away 99.99% of everything they see, the raw data left over is still so massive it honestly defies belief. They require 280 petabytes of active disk storage just to analyze it. And for the permanent preservation of this hard-won cosmic truth, they use physical magnetic tapes. Yep. Old-school tape. They have 340 petabytes of data perfectly recorded onto magnetic tapes simply because it remains one of the absolute best, most secure ways to permanently store massive amounts of information without any risk of corruption.
So you might be wondering, why go to all this trouble? Why build Earth-sized virtual lenses or bury 340 petabytes of tape under the Swiss countryside? Well, because scientists are hunting for a tiny crack in our current reality, the Standard Model. See, the Standard Model of particle physics is almost annoyingly perfect, but we know for a fact it's flawed because it fails to explain dark matter, antimatter, or even gravity. We are perfectly preserving all this data with such strict integrity because we are desperately looking for the one collision or the one gravitational wave that finally breaks the rules.
We're pushing our engineering to the absolute limit to ensure that when we do capture an anomaly, whether it's from a supermassive black hole 53 million light-years away or a tiny fraction of a proton colliding in Geneva, we know, without a shadow of a doubt, that the data is real. Our tools are finally ready to capture the absolute integrity of both the cosmic macro and the subatomic micro. So the only question left is this: when the Standard Model finally breaks, what new universe is the data going to reveal?